Hello folks and welcome back to ECMath. This is a continuation of the video 3.1. The other one was getting really long, so I thought we'd cut it at a certain spot and continue here with talking about interest and compounding, which is just an application of an exponential function, but we're also going to look at where e comes into it, because this is how e was basically invented. And so if you want to know a little bit more about that number e, or just how interest is calculated on, say, your student loans, watch this video. Here we go. So the first way that you might calculate interest is just once a year, compute a percentage, a fixed percentage, and add that on. So for example, you have a student loan, $10,000 at 6% yearly interest rate over a 20-year period. So, the basic thing you might do is you take your $10,000, that's enough zeros. You might multiply by 6%, so think about that percent as a decimal. All right, that's 600. Then you'd add that to $10,000. Where is it? That's now how much you have for the second year. Then you might multiply that by 0.06 again. Get the new value. Add that to your old value. That's your second year amount that you'd owe on that loan. And keep on going. Now, if you wanted to do this 20 times, I guess you could do it in a spreadsheet. It doesn't seem very fun. And in fact, there's a much easier way. So what I just showed you is something you should probably never actually do as a calculation. Instead, to model growth, you can do this equation. We'll just say interest equals the principal, which is the initial value, so that'll be 10,000. Times 1 plus r to the t. And r here is the rate as a decimal, and t is the number of years. So in this case, we'd have interest equals, actually, well, we'll just call it interest, but really it's not going to be just the interest. It's going to be everything that the loan has grown. 10,000 times 1 plus 0.06 to the 20. Now, why does this work? Well, let's simplify this a little bit. This is still 10,000 times 1.06 to the 20. When I multiplied by 0.06 and then I added 10,000 again, I'm really doing in two steps what I could have done in one. This is the same as just multiplying by 1.06. So, and I'll prove that in the calculator. I could do 10,000 times 1.06. The 1 represents what's already there. The 0.6 represents the 6% growth. Hey, it's the same number. So adding that 1 sort of encapsulates everything about having the rate as a decimal, but still letting us use it in an equation. And then since I can now do that in one step, I just have to do that times 20 times to represent the 20 years of the loan. So that's simple interest. Let's actually calculate the value because I think it is shockingly large. About $32,000. Now, obviously, this is really a simple calculation because you would be, if you took out this loan, you wouldn't be paying it all back at the end. You would be paying it back over time. So hopefully your interest is shrinking as you pay some of it back. And also, depending on what type of loan it is, the interest rate might be variable. It might be small. 6% is a pretty big interest rate. If we were talking about savings and you could get 6% on the stock market, you should get 6% on the stock market because that's actually quite a lot of growth over time. But as an example, that's how you compute simple interest. We're going to use this example, even though the numbers are like a little bit unrealistic throughout the rest of this video. I'll say it's approximately 32,000. But I'll keep it up in the calculator. Okay. Most loans or investments or whatever do not calculate interest this way. Instead, they do something called compound interest. And I've written half the interest rate, twice as many payments, not because folks will calculate it that way, but that sort of encapsulates the idea. Basically, if you took out this loan and you wanted to pay it back in the simple interest calculation, you'd be paying one big check to the loan company every year. Most people don't like to do that. Most people like to have their interest, their payments, whatever, bills, split up once a month or every season or something, right? Split it up so you don't have to make one big check. It's easier to budget. It's easier to save. So loan companies will kind of offer this idea. But if you just paid twice as much, well, obviously you're not going to pay twice as much. So they say, okay, why don't you pay, twice a year? So that's twice as many payments, so we can do half the interest rate. So this is more like how a loan would actually be, set up and discharged. So a $10,000 student loan at 6% yearly interest over a 20-year period, compounded twice yearly. Basically, that means they're going to give you a 3% rate, but they're going to charge it 40 times because it's 20 years times 2 per year. Now, we can use the simple interest formula with these values, and that's the first thing we'll start it. So we'll say that's 10,000 times 1.03, so that's 1 plus 0.03 to the 40. Now, let's actually compare what that gives us. And in the calculator, it's a difference of, right, so we've calculated in the same way. It's something that they might offer you as something more convenient to pay twice a year of a smaller amount. But look at the difference here. It's about a $500 to $600 difference. So that's 30 to 620. And let's see what would happen if you wanted to make a monthly payment on this loan. So if we have a 6% yearly interest rate over a 20-year period compounded monthly, that's 12 times per year. So I would need to do 20 times 12 is the number of payments. And the rate is 6% divided by 12. So that's going to be a 0.5% rate, which is going to be, so right, if you did 0.06 as a decimal over 12, that's going to be 0.005. Sorry, not 2, but 5 as the rate. Okay, let's crank that into the calculator. Okay, so I'm about to put all that information in the calculator, but so I have the initial value of 10,000, which is slightly off the screen, times the interest rate as a decimal, which would be 0.005, to the 20 times 12, because that's the number of payments. But I've chosen to kind of leave it unreduced because I'm trying to derive a formula. So I have the rate divided by 12 over there, and I have the number of payments. Let's actually see what that would yield. About 33,102. So that's about 33,102. So if you compare that to the original simple interest, it's actually about $1,000 in difference. We went from 32 to 33,000. And I know these numbers, again, are just estimates, but the difference in compounding with the same loan and same nominal rate, same advertised rate, can actually be pretty big. So what is a formula for compounding? That seems like what we want, right? Like, what is the formula? And then we'll go back and now plug the formula into this here. So compounding. So we'll say A for the amount is the principal. So I was using I. I'm going to switch to A because that stands for just amount. Principal times 1 plus, so we need the 1 to give us the rate as a decimal. And we'll do rate over n to the nt. So 1 plus r over n to the nt. N is the number of times you compound per year. Assuming the unit of time is years, there could be units of time that are not years, but it's usually years. T is the number of years. This n is the same as that n, so you have 2 of those n's in there. R is the rate as a decimal, just like with standard simple interest. And P is the initial value. So this is the general formula. That's kind of what I was typing into the calculator. And if I use that on the example above that we already got as 33,000, the formula that you would use is 10,000 times 1 plus 0.06 over 12 to the 12 times 20, which is exactly what I typed in earlier, and it gave us that, that value. Here, we'll box that. And we will definitely box this. Maybe, kind of. Okay, I fixed my box. So that's your compound interest formula. If they say it's compounded monthly, then n is 12. Whoa there. Monthly, n is 12. If they say quarterly, that's 4 times per year, n is 4. If they say daily, it's 365. Probably monthly and quarterly are the two main compounding intervals that you'll see those, so those are the two to consider. Also notice that if n is 1, that you compound once per year, then this simplifies to the simple interest formula. So it also is just useful for regular interest also, if you'd like to use it that way. Now, one formula you might see or have seen is something called continuous compounding. That is not, if you compound that, you sort of compute the interest rate or add value, not at any specific intervals like every month or every day, but actually every second, every millisecond. The formula for continuous compounding, maybe you've seen it before, is A equals P E to the RT. And this will give you that compounding continuous property. But I always thought it was mysterious that doesn't look at all like the other sort of interest formulas before. Just to recap, P, here's the initial value. E is E, right? So this is not a variable, this is E. R is the rate as decimal still. And T is the number of years. And this is like a little bit goofy, and we'll probably explore this more when we get into logarithms and start playing around with those log base e's. But remember that e is like 2.7, so we are still experiencing exponential growth, because even if the rate is a decimal rate, e to the r is going to be greater than 1, so we're still looking at some exponential growth. It's just, how does that come in? Where does that e come from? Well, I think I'll show you. This is a cute little proof, and if you don't feel like seeing a mathematical proof, you'd like to just accept it, fine. But I'm always curious about where things come from. So let's take a look at why an e is in the continuous compounding formula. So remember from the last video that e was defined as the limit as n goes to infinity of the quantity 1 plus 1 over n to the n. And it doesn't have to be n, it could be any other letter you want in there. And you might be looking at that and say, that looks like the compound interest formula. Kind of. Sort of. Right? But there's a 1 there and there's an r there. So where is everything coming from? Why? How does the e specifically get there? Well, check this out. We're actually going to use some of our cool fraction math tricks. So I could write this as p times 1 plus 1 over n over r, right? I'm taking the reciprocal of a fraction like this. 1 over n over r would be r over n to the nt. Now, why would I do that? Well, it turns out that we kind of need to identify some r's in this formula, and I need to get an r up here. So I'm also going to take this nt and multiply it by r over r. And I can do that because r is not 0, and this will just reduce. So since r is not 0, that'll just reduce out, so that I can actually add that r without changing it. Now, there's kind of a tricky step. So the p stays the same, the 1 stays the same, and I have 1 plus 1 over n over r. I'm going to kind of just like put that in a set of parentheses as and treat it as like its own little box for a second. And then I can rearrange this to n over r times rt. And then specifically, if you have exponents multiplied together, you can think about them as powers. So of powers of powers. So this is really like something to the n over r to the RT, right? So like I'm putting a bracket there because this is really thinking about this as an exponent of an RT. But I have this n over r in both places. So really I have something like p times 1 plus 1 over, what if I just call n over r, h, 1 over h to the h. And then I have that, oh, those are parentheses. Then I have that to the RT. Well, if I now take the limit as h goes to infinity of this, which is maybe a step you haven't seen before, but bear with us for a minute. You're basically saying let h get very big. This is E. So then we get P E to the RT. That's the Pert formula. So that's when we say E is the result of continuous compounding. It's because if you take the compounding formula to its extreme and do a little algebraic trick, basically like a fraction math and multiplying by 1, you can get E into that continuous growth formula. So I hope that trick was interesting to you. There is some other errata, like we have to think about how h is equal to n over r and how that grows and stuff, but we can worry about that another day. But this is kind of the broad stroke of it. So that's where the E comes from in the compound interest formula. So just maybe to go back to where we were, if we were continuously compounding, taking interest every second, every millisecond with our $10,000, now this would be like not a very wise loan to take out. You'd be 10,000 times E to the 0.06, because we use the rate as a decimal, times 20. Let's see what we get. There is an E to the X button, by the way. I'll highlight it. It's right here, so you can just do boop, and then we do 0.06 times 20. 33,201. So compared to compounding monthly, this is a difference of about $100. Compound interest, continuous, and the sooner, the more often you compound, the higher the formula is going to be. Now, in the case of a loan, you obviously want less. Say you're investing in the stock market, though. Maybe you want continuous compounding, right? That's something where you have not discrete intervals, like a stock market that just grows or shrinks, as the day goes. That may be better modeled by continuous compounding. If you are modeling, going back to the other video, we were talking about diseases or populations, continuous compounding might better model that, because it's not like a population of rabbits waits until 12 p.m. on January 1st to have rabbits. They might compound or grow continuously. So that's why this formula actually is probably one of the most used in just general broad circles, even if it's not used very often for interest. All right, so to recap this short-ish video, we have 3 types of interest. We have simple interest, which is just 1 plus r to the t times the initial value. We have compound interest, which involves splitting up that interest rate and then increasing the exponent to match. And we have continuous compounding, which represents splitting that interest rate up infinitely and then computing the exponent infinitely, and it turns out E gets built in there. And we compared, I lost it. We compared the same imaginary loan at these different schemes and saw that the more times you compound, the more the value increases. All right, folks, let me know what questions you have. Thank you all for watching, and I will see you all again next time.